for Mother Earth.
지구를 위해서.
Für Mutter Erde.
Pela Mãe Terra.
Heard around the world, welcome to the Rock Talk podcast with your host, Dave Stein.
Hey everybody, thanks for listening here. We have a special guest today, Sudhir Murthy. He is a world water expert over here going to be discussing with us about some of the water innovations, especially with wastewater treatment. I'd like to introduce him here today. Hey Sudhir, how are you doing today?
I'm very good, thank you. How about you?
I'm doing great. It's beautiful weather out here today.
It certainly is.
Would you like to give us a little quick background of what you've done and kind of where you've been with this industry?
Well, I've been in the water sector for about I would say 30 years now. I started my career in the water sector when I did my master's and then later on PhD at Virginia Tech, and then I really worked in the consulting sector for about 6.5 years at two different consulting firms, Parsons and CH2M Hill, and now they're called Jacobs. And then after that, I worked at DC Water for 16 years until last May of 2018. And then I decided that I'm going to take a turn and try something on my own. So I'm more or less right now an entrepreneur and trying to create new commercial approaches in the water sector.
Okay, that's very awesome. I got to say, let's go Hokies. I went to Radford, so a lot of my friends went to Tech. So, I'm a big Hokies fan as well.
Great, thank you.
So I like that you've worked at the DC Water, and I know you've been kind of talking about some more of the steps to innovation in the water industry, and I just kind of wanted to touch. I know you had put out some papers on that, and I just wanted to touch on what are exactly the steps that people should understand that it takes to create innovation in the water sector. I know a lot of people sort of may not understand the entire process or kind of what it takes to get water treatment or water quality to where it should be.
So a lot of people talk about water sector and how slow it is to innovate, and usually what I do is I try to understand better what are the inner workings and the fundamentals associated with innovation, and this I try to do that more from my own understanding, but then to try and maybe help others understand it better. And if you look at the water sector and you go to a treatment plant or something in the water sector, you'll find that no two treatment plants look alike. They are all quite different, but they're also in some ways similar. And so, why are they different and why are they same? And what are really driving these differences and similarities? And so, what I did was I kind of to make it easy to people understand. I like to think laterally, and so my lateral thinking really came up with three different animals. I call them the hare, the horse, and the elephant. And the hare is an animal that, as most people know, lives for about 5 years and matures, and its gestation period is very short, maybe less than 6 months, perhaps, maybe a year. And then there's a horse which lives perhaps for 20 years, and its gestation period is somewhere in the middle, maybe a couple of years. And then there's the elephant that lives maybe for 80 years, and its gestation period is in the maybe 10 to 15 years time frame. And so I think of the different technologies in the water sector as those three different animals. We have these really what I would call them concrete infrastructure, the traditional concrete and really buried infrastructure even, uh, that last for a long time because concrete doesn't go bad that easily. And so those are what I typically call the long-lived elephants of the water sector. They last for 80 years, and they don't go obsolete that quickly. And so they have a different life cycle of their own. You can imagine the aqueducts that were built during the Roman Greek times. Those aqueducts lasted maybe even about 1,000 years, right? And so those are really long-lived infrastructure. And then you have the age of the machines, right? And uh, and and those are equipment, whether it's hydraulically driven or mechanically driven or thermally driven. They last for about 20 years usually, maybe give or take. And so I call them the horses. And uh, and, and 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 really, a lot of the patent laws are built around the horses because if you think of patents, they last for 20 years. And if you think of what we call the industrial revolution, they were built around the horses, lasting 20 years. And then they go obsolete, and so you can think of the cycle there. And then more recently, with the intelligent systems that are there, you can think of the iPhone. And those are the same things in the water sector. You have sensors and controls and all of that in the water sector for detecting and controlling different processes, for maintaining different equipment. Those I call them the hairs. They go obsolete maybe in a 5 year time frame, while on the other hand, their gestation periods are very short. And of course, within the water sector, we don't know how to procure hairs. So we sometimes procure hairs like we procure horses. We install hairs like we install elephants, and so there's a little bit of confusion on obsolescence rates and how do we actually manage the procurement of these different technologies. And also on the supply side, no hare wants to call himself a hare or herself a hare. They would like to be an elephant, and so they mask themselves as elephants. A good example is the AMR system for water meter reading. And what went obsolete first was really the hair. The reading the water meter using a radio, and now you can read the water meter wirelessly, and it was the hair that went obsolete, and not the horse or the elephant. And so, how do I manage? And usually these hairs are coupled with a horse, and so do I actually replace the entire hair and horse, the meter itself, along with the portion, the radio system that went obsolete, or do I actually start thinking about how we install infrastructure in the water sector? Do we install it in horizontals? Do we install the elephants, and we can replace the horses, the machines and the hairs interchangeably in different time cycles? And so, how do we procure it, and then how do we create the standards associated with managing these different technologies? Um, and so that's a thought process that needs to take place, regardless of whether you're buying something or you're inventing something.
All right, that was very informational. I appreciate that. So, what would be some of the steps that are going to lead us to innovation in the water sector, and what's the most important part of these steps that you think? I know you that everything does not happen by one person. Is having a collaborative team effort one of the more driving factors that's going to create change in the water sector?
Yeah, so there are two areas there. One is really uh, where does one want to go? Typically, and historically, uh, there's this perception and maybe a reality that there's a supply side of the a sector and a demand side of a sector. For example, in Boeing and Airbus could be the supply side of aircraft, and United Airlines could be the demand side of buying an aircraft, right? And or American Airlines for that matter. There's the same thing in the water sector. The utilities usually are on the demand side, and there are lots of different manufacturing companies on the supply side, and that's been very normal, and it's still how things work today. But if you really want to speed up the gestation periods associated with new technologies, the lag time, it's sometimes useful to actually work with the supply and demand side together, right? And do it jointly, and then you can speed things up. You have to create the right incentive processes. It's we are humans are very subject to behavioral tools, behavioral approaches, and so if we create the right environment for people to innovate jointly, then actually you can speed things up. And so the open innovation process really is really what I would say is to find ways and tools and find ways and tools to speed up the innovation process and and to do good. And how do you actually go about doing that? A lot of it, people think of open innovation as writing a good contract, but that is, I think, uh, the element that probably distracts from the open innovation process. But most important for open innovation is how to create trust amongst people, and to work as a team, and so to build those trust and team efforts really takes a lot of time and a different mindset. And so that's something that I did a lot at when I was at DC Water, was to create those frameworks of cooperation uh, amongst different groups.
Okay, that's exactly where I was hoping we could touch on next with some of your time at DC Water. I know you had quite an impressive career there, and myself being one of the people that benefits from any of the innovation that DC Water has. So I know we were discussing a little bit before this about some of the things you had done, and one of the topics that I think struck me that was very impressive was the use of energy neutral wastewater treatment. Now, is this something that you worked on and you developed at DC Water?
So it's a combination of things. I still work on it right now. Um, the whole notion there is uh, over the past say 100 years of wastewater treatment, as we call it today. People also call it water reclamation. Uh, um, in the past 100 years, uh, the the whole concept of how one built and managed the treatment process was really revolving around uh, doing that exactly what it said, treatment. And so you remove the pollutant and put clean water into a river or a lake, which is great. But often uh, when we put a series of steps together, um, the steps did not work together in a what I would call it a virtuous cycle. In fact, the way things often worked was was these steps really worked against each other, and you ended up needing a lot of energy for treatment, and also a lot of space. It wasn't space efficient. and it wasn't even energy efficient. And so there were these large treatment plants being built that weren't very space and energy efficient. And you can think of this: most wastewater treatment plants uh, may have started off being in 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 uh, in urban sectors, in not so very nice locations, but they were always next to a river or a lake, because that's where we would discharge water. And over 50-year time frame, most of these wastewater plants are actually in the best location, because people want to build their houses or recreation around lakes and rivers, and there you have a wastewater treatment plant consuming a huge amount of land, and and not very efficient. And so how do you actually design in the future different types of wastewater treatment or water reclamation facilities that are a little bit more efficient in terms of how much space they need, but also how much resources are used? Because with the changing climate, we certainly want to make sure that we are using less resources for doing a treatment. And so that's really the basis for why one would think of energy neutral processes. The other basis is, just to give you a context. If you think of the world today, about 1 billion people have access to a reasonable amount of wastewater treatment. But I would posit that in the next next 2 decades, or maybe even within the next decade, another 2 to 3 billion people will have access to reasonable wastewater treatment. And so in this next decade, and I have called this the golden age of water. Uh, in the next 2 decades, uh, really we're going to have maybe quadrupling of the infrastructure that's there today. And uh, and so uh, so if we are going to quadruple it, how do we learn from what we've done in the past, and what do we actually look to do in the future? So if you typically look at what you do in the water sector, wastewater treatment, basically you manage the water itself. So water is itself a resource, and how you manage that resource is important. But then within the wastewater, within the sewage, you have basically three different elements: carbon, nitrogen, and phosphorus. And these three elements are usually in the ratios of 100 to 10 is to 1. So for every 100 parts of carbon, ballpark, you have 10 parts of nitrogen and then 1 part of phosphorus. And uh, and and uh, and and they are and these are nutrients, and so they impact the water in the same ratio. So sometimes 1 part of phosphorus is as bad as 100 parts of carbon. So because that's the eutrophication that occurs in the lake and river. And so how do you manage these become important. And really, today, the hot topic is, how do you manage these three cycles: the carbon cycle in the plant, the nitrogen cycle within the plant, and the phosphorus cycle in a much more sustainable manner, but at the same time, do it in a very compact plant. Uh, so how do you drive convergences between intensification of treatment, doing it in a compact plant, but also doing it in a much more resource efficient and sustainable manner? And to do that, uh, really, it's to work within those three different cycles, and managing the cycles in by using as little energy. I'll give you an example of carbon. Um, uh, when we manage carbon, uh, carbon has in sewage is usually reduced carbon. So there could be, say, for example, fats and proteins in the sewage that come from human waste. And these reduced carbon have a lot of calories, right? Because that's what we consume. And so there's a lot of calories in the wastewater. And most wastewater treatment plants, they add energy in terms of oxygen, huge amounts of energy in terms of oxygen, uh, to remove energy from the chemical. So we add electrical energy using these large blowers uh, to destroy chemical energy. So it's actually becomes a double negative. So how do you actually change things around and use as little electrical energy possible, and then send the chemical energy to make methane gas and then to drive engines, for example. And so the carbon balance is really about redirecting carbon to energy producing processes rather than destroying that energy using electrical energy and air. Uh, and so if you look at most of the wastewater plants in United States, uh, it's this double negative that's happening there, where a lot of electrical energy is used to destroy chemical energy, and how do you actually change things around? And so we've started looking at developing new technologies. We call it carbon redirection technologies, where we redirect as much carbon as possible to anaerobic digestion, and then only send the amount of carbon that's needed downstream to other treatment processes. And so manage that, you really need to work with the different types of carbon in the wastewater. You have what we call particulate carbon, we have colloidal carbon, and we have soluble carbon. And how do you actually manage those three different types of carbon, and do a good job of it? The same thing with nitrogen. Nitrogen, the reduced nitrogen compound is ammonia. It's got energy in it. When anything has got hydrogen bonds, it usually means it has energy and calories associated with it. And so you can use the energy in ammonia uh, uh, rather than destroy the energy in ammonia using oxygen. So right now, most of the treatment processes destroy the energy in ammonia using oxygen, and the question is, how do you actually do a better job of managing the energy in ammonia? And can we actually use the energy in ammonia by recovering it directly, or on the other hand, to perhaps use different types of bacteria. In this case, you could use an anammox organism or a shortcut nitrogen process to manage that energy in nitrogen. And then finally, phosphorus. There's lots of really interesting research being done in phosphorus, especially the whole concept of what people are today calling aerobic granular sludge. And so how do you create really compact plants using the concept of aerobic granular sludge that has basically a central core that contains these phosphorus removing organisms of the granule, and and then work within the context of these organisms and the morphologies of these organisms to actually uh, build very compact plants. But then the phosphorus can be recovered uh, as true white, or as brushite, or as hydroxyapatite for agriculture. And so you recover the phosphorus, uh, and how do you go about first removing it from the wastewater and then recovering it? And so you have the carbon cycle, nitrogen cycle, and phosphorus cycle happening in the plant. And how do you actually do a good job of recovering these three elements, either recovering or using it in a good way? In the case of carbon, maybe you can create natural gas and pipe it, or you can burn the methane and produce electricity. In the case of nitrogen, how do you actually do a better job of managing it rather than add a lot of air to convert ammonia to nitrate, and then you need a lot of carbon to convert nitrate to nitrogen gas. And then in phosphorus, what do you do in terms of growing the right bacteria and the right morphology to remove the phosphorus and then to recover it? So that's the essence of energy neutral wastewater treatment, is to build compact facilities. And I'll give you a sense, when you remove carbon early and redirect that carbon to, say, anaerobic digestion, the downstream processes that you typically oxidized carbon becomes much smaller, and because the inventory of carbon going to those processes are less, and so now you need a smaller process. And so actually you create a virtuous plant from a perspective of it's a small facility, while at the same time it actually becomes energy neutral.
Okay. Yeah, that's very interesting. I'm curious to understand a little bit more about this and where are we at with DC water and their ability to kind of start to utilize a plant in a more efficient manner. And I also want to tail onto that question with, is this technology something that you think, if implemented in maybe these developing countries, would be able to get them off to a much better start a lot quicker now with this knowledge and creating a more compact, more efficient facility to have them process their water and allow the more developing communities to have better access to treated water?
Yeah, I really think it is in many ways an approach to leapfrog. In the first part of our conversation, I talked about the elephants, right? When you build infrastructure to last for 100 years, it's really too difficult to suddenly say, okay, I'm going to break it up and change it and do things differently. So a lot of what we've been trying to develop as inventions, one is to how do you actually use the same infrastructure uh, to do something different, uh, and second, how would one leapfrog, um, especially in emerging markets? How would one leapfrog and actually do things differently? Um, and a lot of this leapfrogging is really managing risk. No one wants to build 100-year infrastructure by saying, "Oh, I'm just going to leapfrog what was done for the previous 100 years and do something quite different." It's very difficult to have that mindset. So how do we create transitional approaches that allow you to do multiple things, and while at the same time create a reasonable approach for leapfrogging? Give you an example. There's a tank in most wastewater treatment plants in the United States called the primary tank, primary sedimentation tank. It's usually a rectangular or a circular tank that has a retention time of about 2 hours. So water stays in that for 2 hours, and in that 2 hours, particles, particulates. I mentioned that wastewater contains particulates, colloids, and soluble material. The particulates typically are removed, with about a 60% efficiency in that primary sedimentation tank, and so you have that efficiency, and that's the tank. Now, can I actually do something different with the tank? And so we have developed a process called the AAA process, for example, and that's something that I've been commercializing, where I convert that primary tank. I put a little bit of air piping at the bottom, and we convert that tank into a biosorption tank. And what that biosorption tank does is it removes the soluble material as well as a particulate material, and then sends it to anaerobic digestion. And so now I'm managing my fractions, my carbon fractions, more efficiently by converting the primary tank into a biosorption tank, and to send less carbon inventory to the downstream process, while at the same time um, send more carbon to a more efficient digestion process to produce more gas and then energy. And so that's one example of a technology where, rather than say I'm going to build something completely different, it is quite different, but I use the same infrastructure to actually make those differences, and so it allows for a more seamless transition from an existing infrastructure to a new infrastructure. And so for plants within the United States that already have that infrastructure, it'll help uh, them transition, and then for the plants that are not built yet, it gives them an approach where they manage risk, meaning they're not doing something completely new, because they can always default to an older process or older approach if they worry that it's not going to work. But then it is fundamentally different in terms of how you manage your carbon streams. So that's an example of how to actually work within the old and the new.
Okay, nice. So there's a way where we can build on what we have already and use that to kind of transition and still upgrade our process and our technology, which is kind of interesting. And I'd like to figure out a way to get some of that spread around the country. I feel like that could be a great benefit to a lot of people.
Yeah, and so if you look at a lot of our inventions, it's really about how do we make use of our existing infrastructure, and really the inventions that have come out are really what I'd call it demand side perspectives of how to change things without change things fairly fundamentally and quite radically, but using some of the same infrastructure that you may have, and so so uh, so it makes it easier for a utility to manage their infrastructure in a more seamless way. We have a technology, we call it indents, and in that technology, I mentioned to you aerobic granular sludge before, and so how do you actually create aerobic granular sludge within a plant that didn't have it, and so the indents concept uses a combination of processes, technologies that you can just adapt into an existing biological treatment process. For example, it includes a hydrocyclone manifold and proper zoning. And if you do the zoning and the manifolding, then you can convert it into a much more compact process, and double the capacity, or maybe increase the capacity by 50%, between 50% and doubling the capacity. So while doing it in that same infrastructure. Um, so that those are the concepts that we've really been working on. We've also been working on smart technologies. How do we use better control approaches using sensors, um, and to drive much more intelligent water systems? A lot of people talk about analytics, and how do you use artificial intelligence? Uh, Artificial intelligence typically use stochastic approaches to drive for answers, get your answers. Or you could also use deterministic approaches to get your answers. And so, the stochastic approaches are more black box, while the deterministic approaches are, maybe you can call it white box. But so, what are the gray box approaches that that could drive us to our right solution? So that's something that I've been interested in. Is how do you blend the right deterministic and stochastic approaches? And so, can we bring in artificial intelligence while at the same time use some fundamental knowledge that we have about certain processes, and then use the AI associated with those that we don't know too much about.
That was going to be my next question, was with all this development in recent technology, is, and especially with the development of AI, is that something that you think is going to have a great impact on the ability to treat water, the ability to manage everything better? If you can have a system that has a in-depth analysis sort of calculating every second of the water as it's being treated, is that something that you think will allow us to take treatment to the next level?
Yeah, so I see AI coming in two different ways, waves. I would say the first wave of AI is really going to be, I believe, in smart maintenance. Um, a machine is like a car. In the good old days, uh, you change your oil every 3 months, right? Or a certain number of miles, and and then some of the cars today will say, hey, it gives you a warning based on some some prognostics, and it may just be a time prognostic, but there may be other prognostics and sensors that say, hey, something is wrong with your car, and you need to change do something different, or oil, and or something else. Um, and that's the same thing, I would say, in a plant. We have lots of machines, centrifuges, you name it, and if something is going off kilter, how do you actually drive the right prognostics? It's much more so than just preventive maintenance. It's how do you sensorize the technologies to actually give the right prognostics, and so it's less about operation, but more about, when do I go through a certain maintenance cycle associated with a process. And I think that's already taking place, and that's going to really revolutionize how we maintain our plants. I think of the five senses that we have as humans, right? Um, the touch, the touch is really a vibration monitor, right? The eyes are a camera. So how do we use our five senses? But really, in the context of a wastewater plant, a sensor for ammonia is much more like taste, right? And so how do you use AI as we use our five senses, but much more in a seamless way to do those prognostic maintenance. Um, so that's going to really happen first. The second wave is going to be more in the operations of the plant itself. Uh, uh, I think that's going to come after, only because uh, there are different time cycles. A maintenance of a something is over a time cycle of, say, days days to months to a year, right? While the operation of a plant has got a time cycle of minutes and seconds and hours, and so it's a little bit more complicated, and so it'll probably be the next to adapt rather than the first to adapt. um, and so that will take place. Um, and that's really what I look forward to in the next decade or so.
Yeah, I think the invention of AI, and like you're saying, I didn't even ever think about the maintenance factor of how that would come out to play first. And after kind of hearing that, it kind of makes complete sense that we would sort of want to use that to get the maintenance features up. And I definitely can understand
And
that.
you can see that in the car, right? The maintenance of a car, the prognostics associated with the maintenance of a car came first, and then only recently is a self-driving car coming in. The operation of the car is coming after the prognostics associated with the maintenance, and and they were maybe several decades apart. And so I maybe it's not going to be several decades apart for a treatment plant, but certainly uh, I think we're going to have a lot of experience associated with, and comfort associated with AI, with maintenance, before we actually do a lot more with operations. And then the other thing that I see happening is better better platforms. Uh, you know, so right now, when someone tries to sell a utility, some application in smart water, um, uh, you know, there are something like 50 different applications that are in the smart water area, and none of them talk to each other. They are all, if we need to maintain them, we become captive to the person that's installing that smart water technology. And so how do we actually create these platforms, like the apps on your iPhone, where if I'm done with that app, I get rid of that app and put a new app in, right? That cannot be done so easily in the water sector anymore, because every new smart technology that's installed is almost like de novo, and you're captive to that person, uh, uh, because it's all verticalized. and so if I'm going to spend $1 million on a smart technology that might not integrate itself well with other things in other smart technologies, how do how, what do I do differently? And so what we really need, and I tell you, in the water sector is much easier than other sectors. Is what we need is good standards on how we actually build the smart infrastructure in the water sector. And the reason it's easier in the water sector is, to a large extent, it is a public sector. So our ability to drive standards doesn't have the competitive pressures in, say, for example, the energy sector, where maybe two energy companies may not talk to each other. Two water utilities or a bunch of water utilities might easily talk to each other to create the right standards. But standards in the smart water sector are quite urgently needed, because without those standards, it's hard to actually build the infrastructure that allows for easy replication, managing obsolescence. All of that becomes easier if you create the standards.
Now, what would you say is stopping most water treatment plants from utilizing these new techniques to better manage the energy and create more of an energy neutral process? Is there something that is kind of holding them back, perhaps funding, or maybe is it just lack of knowledge, or is it something that most treatment plants are actively working towards?
Um, I think it's really trying to figure out what is needed. Within the United States itself, energy is quite cheap. In a water utility, energy may not be the big driver, and it may be labor that is more expensive, or there are different aspects that contribute to a large part of the operations of a plant. So I would really look to understand what is driving water utilities. For example, resilience. The whole concept and notion of resilience uh, is perhaps more important than something abstract such as climate change adaptation. Uh, if you tell someone, I want you to adapt to climate change, that sounds that doesn't ring a bell. But if you talk about resilient structures, uh, then that's different. So you really need to work within the context of what are really the drivers for a water utility, um, and to work within the context of the drivers.
Now, let's just pretend we're in the general public, we're your average person. We do care about our wastewater treatment and we want to do what we can to help. What is one thing that you would say is the best thing that your average person could do to kind of help alleviate sort of the issues or pressures of wastewater treatment, if there is anything that your average person can do?
Um, uh, what I would say in the near future, um, the amount of micropollutants that are coming into the wastewater are going to become more and more important. Um, uh, I mentioned the three macro pollutants. Wastewater are carbon, nitrogen, and phosphorus. But there are micro pollutants, and so how do you actually manage what you put down the drain? Um, is will become much more important. So uh, how do you dispose of your medicines? How do you manage? Um, uh, you know, uh, During Thanksgiving, how do you manage your grease, for that matter? Because grease can block the drains, right? How do you do those kind of things at the micro level becomes important. The other thing that I would say is a trend, uh, is what we would call distributed treatment. And what we mean by distributed treatment, and this, it may not apply directly in maybe DC, a region or certain particular region in the country, the United States. But distributed treatment is a blend of what I would call is centralized and decentralized treatment. Centralized treatment is where everything is sent to a central wastewater plant. A decentralized treatment is like a septic tank. A distributed treatment is where it still has some centralized governance and management, but the treatment is very distributed, and so that is going to become much more common. And so how do you actually manage this distributed treatment for communities where the treated water can then be recycled for gardening or other purposes, rather than sent to a centralized facility? So those are things that are going to um, become more prominent. It's very similar to microgrids that are going to become more important in power generation. The cell phones versus the landlines already took place in the telecommunication utility sector. So I think the role of the future consumer is is going to be bigger than in the past, and I think that's a good thing, because sometimes we just flush things down the drain and say, we don't know what's going to happen, and we don't care what's going to happen, because somebody's going to deal with it. While if it's more of this, what we call a distributed approach, then it impacts you almost immediately, because in the sense of a distributed treatment system, if your system is not working, and so then you can make some changes. So how do we manage those distributed systems in the future? I believe this is where smart systems and AI are going to be hugely important, because uh, I you know. I think of it this way: a distributed system is going to be sensorized, and someone knows that whether that system is working or not, and rather than people are just blind to a distributed or decentralized system like a failed septic tank that is not working. And so if we are aware that something is working or not working using a smart system, that's what's going to drive distributed systems. And those distributed systems are then going to drive the average consumer to become more aware of what they're doing.
Okay, nice. I like the sound of all that. I think kind of as a as a collective community, we should be able to band together and make some good positive changes for the environment and just for ourselves really as well. Now, I did want to touch on a topic I've seen a lot of people sharing on social media sites recently. Talking about kind of the micropollutant side in terms of more like facial wash beads or glitter or little pieces of plastic that are going down. And I'm just curious to know, are those a problem for you guys in terms of treatment? Is that causing issues, as everyone's kind of been sharing?
So, um, from a treatment perspective, there's so little known. There are quite a few papers that have just started coming, have just started being published on say, for example, microplastics. In general, uh, most wastewater plants are not designed to remove nano and nano materials. They're certainly designed, perhaps to remove micron sized materials. But certainly nano sized materials are much more difficult to remove. And how and what do we do associated with the future increase in nano sized materials? Is something that we need to figure out, and we need to create new treatment processes. It's my philosophy is not about banning things, but really to understand new treatment approaches uh, that actually addresses changes in how society consumes and does things. And so we need to figure it out, and we need to do these developments of technology in a way that they are um, sustainable. And so how do we drive development of new sustainable technologies, that remove such kinds of materials? And can we actually do it within our existing infrastructure by making small changes, or do we need new infrastructure? Those are things that we need to figure out.
Now, how exactly do you guys filter out the nanoparticles at this moment in time? Is this something that is filtered out by just a nano filter, something that is, or is this, like you're saying, this is one of the more difficult things to treat? What exactly is the way that we typically would remove these nano pollutants from the water?
So, so, a small particle is for example, a colloid is a small particle, and a colloid could be anywhere uh, from a molecular weight of 10 to 30,000 Daltons to a micron size of say 1.5 micron or 2 micron. So anything between that range of say 2 microns to a molecular weight of 20 to 30,000 Daltons, or maybe even as low as 10. And so uh, the these small molecular weight material are certainly what I would call perhaps in the nano size. And so how do we manage those small material? And if you look at our treatment processes, there are basically two approaches we've used in treatment to remove colloids. One is a concept called coagulation that's been used for a long time, where we use chemicals such as iron and aluminum, alum, for example, or polyaluminum chloride, to create what we call a sweep or charge neutralization of these materials. So if these nanomaterials are charged, you can actually neutralize the charge and then destabilize them, because the stability of that material is based on charge. And if you destabilize them, then you can remove them, or you can sweep them into the coagulating mass, and remove them. The other approach is actually to use filters, uh, and more and most drinking water plants. In fact, nearly all drinking water plants have filters, usually sand filters or anthracite sand combination. Some do actually even have granular activated carbon in the filters. So there are different filters and different media associated with the filters that can remove different sizes of particles, and as well as different uh, with different efficiencies. And so the filters can also remove these material. The coagulation process can remove some of these materials, but how efficiently they remove it and how can you actually improve that efficiency, it really needs to be further studied and researched. And can we actually develop new technologies, just perhaps technologies to uh, uh, you know uh, remove these materials using classification? um, that's yet to be seen. So what I mean by that is, can I just use a membrane, for example, to remove it in a very large plant treating a lot of water? It's hard to actually put a huge number of membranes, because for membranes, you can't scale it easily. You just need a lot of, right? And uh, so we really need scalable technologies that can scale easily. And
Pardon this 15-second interruption. As we know, humans are tainting the water, and the technology we use to produce GeoWonk's Rock Talk podcast has had a moment of interruption. Now back to the show.
Art, I think we were talking about how you were talking about how it needed to be a scalable technology, and for us to.
yeah, so I think I was there close to the end. So how you can get economies of scale. uh, uh, in building technologies to remove nanomaterials, and how you can do it at in a large facility, a large centralized facility.
Now, let me ask a question. I am curious here. Actually, I'm curious if you've had any experience in the 3D printing industry and if that could be something that would be useful in terms of maybe being able to print a nano-sized filter. I know right now I'm actually a partner in a 3D printing firm, and we are printing at about 2.5 microns right now. So I'm just curious if that's something that might be plausible in the future, where we have a literal just a nano-sized filter filtering out particulates that are even smaller than 1 micron.
Yeah. From a distributed treatment perspective, that certainly could occur, right? You know, sometimes what you see, say for example, in laundry, they may use nano silver in a laundry in a clothes, or you could use a certain nano size uh, deodorant that ends up on clothes, that then is laundered. Then it has this large pollutant loads of carbon, nitrogen, and phosphorus, but you also have these nanomaterials. If I'm focusing on removing nanomaterials, uh, how do I actually not remove the carbon, nitrogen, phosphorus, and just remove the nanomaterials? So sometimes we have to just figure out what treatment step takes precedence over other treatment steps. Do I can I remove the nanomaterials before I remove other macromaterials? Or do I have to remove the macromaterials first before the nanomaterials? Those are things that need to be figured out. Usually, in a wastewater plant. Um, uh, Most of the filtration steps, the actual filtration steps, occur right at the end of the treatment plant, um, because you've removed a large amount of pollutant load that could clog the filter, and so if you've removed the load that clogs the filter, then the filter run times are much longer, and um, so those are things that need to be considered.
All right, well, I like the sound of that. It's good news. Sudhir, I wanted to talk to you. I know you're involved with the International Water Association. I just wanted to know if you could spread some light here on exactly what that is and what they kind of do and what is your role there.
Okay, so International Water Association is a member association that consists of professionals. Uh, uh, there are academics. There are people from the practice. From in practice, it could be utilities, it could be consultants, regulators, policymakers, manufacturers. That are part of the association, and usually those that participate in the IWA, International Water Association, have some international hook to their interests. So for example, if you're a researcher, and as a researcher, typically research is done globally, right? Whether it's in Europe or whether it's in China, there's a global interest in research, and so usually researchers tend to participate in international forums, and so International Water Association serves research, for example. It also serves practice. In some cases, if you're a utility in Portugal, and the utility in Portugal is in Lisbon, and the next utility is in Spain, say for example, the neighboring country, and there's the utility is Madrid, for example. Large cities. A CEO from Lisbon might have something common from a CEO in Madrid, which who may have something of common interest with the CEO in Washington D.C. And so we drive a global agenda to help solve problems associated with uh, those that are in the academic or practice fields. and it's usually water professionals.
Wow, that sounds like a really great organization, and it has kind of a great goal. Is there anybody allowed to join this, or is there any requirements to joining this?
There's no requirements. It's just a membership association. There is an annual membership fee, and the way the association is structured, you can join as an individual, or you can join as a company. So if you have a company, the company can join the association, and then depending on the size of the company, you get a certain number of members within that company as a subscription.
Okay, very cool. And exactly what can you end up doing in this? What would your average person be able to kind of put their hands on and help with? Would it get them access to any conferences as well?
Yeah, so there's a lot of eventing. So within IWA, uh, I believe there is um, m- between 50 to 70 events occurring somewhere in the world in 1 year. And so that, to give you a sense, if there are 52 weeks in a year, there is more than one event occurring every week somewhere in the world that is branded as an IWA event. And that's what what we do in terms of events, and they are small and large events. Are Small events are maybe 100 people attending it. Our large events could be as high as 10,000 people attending it. So our recent large event was the World Water Congress in Tokyo with about 10,000 people. Our small events are they occur every week, really, somewhere in the world. Um, and and basically, uh, if you think of the water field, you can divide it geographically. So you can say Asia or Europe or North America. So they are geographical. Uh, uh, Boundaries associated with your where you are from, and the events that IWA have could be a geographic event. So, for example, there's an event that is part of the Asia Pacific region of the world called Aspire, and so that's an IWA event that is for that region. You could have an event that is based on a certain specialty of yours. So if your specialty is, say, for example, water reuse, you could be attending just an event based on water reuse, and you could get professionals from all over the world focused on water reuse. It could be on desalination, or for that matter, or it could be on wastewater treatment, nutrient removal, for that matter. And then so there are events based on specialty, and there's the events based on geography, and then you could also have events based on what you know if what stage of your career you're in. You could be a young water professional, and so we have events just for young water professionals. And because sometimes if you're in an early stage of a career, you want to meet other people within that same phase of that career, and so we have events there. um, and then we have events also for a certain profession. So if we want utility leaders, if utility leaders, say CEOs of water utilities, want to meet and discuss certain governance topics associated with managing utilities, we have events for water utility leaders and such. You could have a manufacturers forum, you could have a regulators forum. So these are usually forums for I guess that could be the word, where different professions can meet. So it's certainly a place to meet, an event. Um, then we also have publications. In fact, what IWA is really known for, and uh, compared to, say, other professional associations, is scholarship. We as an organization are valued for our scholarship, and so we have some really high quality publications, both books as well as journals that come out of our association. Much and more these publications are becoming they're on the web and easier to access, such as the open access journals that are out there. The other thing that we are trying to do, and I've been working on it, is to develop a new innovation platform. I use the word innovation, but what I've been trying to drive there is actually to create an innovators platform. So to emphasize the people rather than the process, and to really work through and bring a collection of people that. Uh, that are bridges between communities and can drive innovation.
No, it sounds like a great organization, and I will be posting the link below for any of you guys who want to go and check out the International Water Association, the IWA. You click the link, and it'll take you over there, and you
Thank
guys
you.
can go and join. All right, Sudhir, I wanted to thank you so much for coming on to the show. This was great, very informational. I really learned a lot about the whole process, and it makes me excited to see the future of where wastewater treatment is going, and kind of really with the innovation of AI that we can hopefully make a great impact and get everybody treated water wherever they need it
Yeah,
across
thank
the
you.
globe.
Thank you for having me on. And um, if you would like me to respond to other questions in the near future, um, maybe we could even create some kind of a LinkedIn. Is that what you do? Respond to questions through LinkedIn?
Yeah, I do through LinkedIn. I actually am going to have a forum set up on here. I haven't set it up yet. I think it'll go live, hopefully before the water talks that I'm going to post. And
Okay.
the whole goal is to kind of make something like you're talking about, where it's like an innovator platform where I'm going to just allow people to share knowledge and stuff. And that could be a great place where, I could have a, okay, Q&A with you and post it up there. And that could be a forum talk based on your podcast. And, you'd be able to answer questions there. Um, and we could definitely do something off of LinkedIn. If I'll post this up on LinkedIn for sure. So anybody who has questions there, you'll be posted on, and you'll get the message and the link to everything. And you can go there and respond to those people. But hopefully, I can get that forum put up on here and set up, and then we can set up a little spot on there for Q&A, and you'll have access to that. So anybody comes, you can go and comment with them and have like an after chat. And I don't know. Do you ever use social media or anything like that? If you want to, we'll get you a shout out for that, whatever, so people can follow you or discuss further with you via any of that. I don't know if you use any of that stuff though.
Really, not too much. I do get on LinkedIn, perhaps more often than any of the other social media. I'm not much of a Twitter guy. Um,
Nah, me neither. So we could just keep it through LinkedIn, and then on the forum through this website that I got going on. And I think that would be best anyway. So, but yeah, no, that would be a great idea. And I'll see what I can do. I'll keep you informed early next week what I want to try and do with that. I'll try and work that in. And I think that would be great, because that's part of one of the things I'm hoping to get to, and is have people that are connected to the site that are available for questions and answering, just sort of like that, maybe even if it's only through forum. But I think it'd be a great way to start getting knowledge really just spread around, and start making like a great collaborative kind of team that can sort of just build, and we can grow it up and have great stuff happen all over the planet, really.
Rock Talk, the podcast, is produced by GeoWonks. Go to geowonks.com and join the community.